The length of New Zealand rivers that travel to the ocean are given in this table, and the Tasman Sea in this table. Do the data provide enough evidence to show that the average length of the rivers that travel to the Pacific are longer than the rivers that travel to the Tasman Sea? Use a 5% level of significance. All right, so our null hypothesis is that the mean of the Pacific ending rivers is the same as the mean of the Tasman ending rivers. And the alternative hypothesis would be that the mean of the Pacific is greater than the mean of the Tasman. Alternately, right, we could have gone mu sub p minus mu sub t equals 0, and mu sub p minus mu sub t is greater than 0. Either one's fine. All right, so we know alpha equals 0.05. Our formula is going to be the two-sample t-test. So t is equal to x bar to the Pacific minus x bar to the Tasman Sea minus 0 divided by the standard deviation, which is the square root of s of standard deviation of the Pacific squared divided by the sample size of the Pacific plus the sample size, or the standard deviation of the Tasman squared divided by the sample size of the Tasman. There we go. So there's our formula. So hopefully, again, I've typed in all my data here correctly. And I'm just going to go stat calc 1var stats on list 1. And I get 131. So I get x bars for the Pacific is 131.15. Standard deviation of the Pacific is 78.9. And the sample size for the Pacific is 19. And then on the Tasman Sea data, we've got x bar for the Tasman is equal to 67.6. The standard deviation is equal to 33.3. And the sample size is equal to 22. Okay, so we should check our assumptions here since we actually have the data. So we want the distributions to be normally distributed. Neither sample size is large enough for the central limit theorem. So let's look at the normal probability plots for list 1. And that doesn't look great. It's got that pretty big bend in it. Let's see, normal probability plot for list 2. And that has a big bend in it too. So we've got some skewed data here. So that's not great. Sample sizes are relatively small. They're almost, and this one's almost 25. This one, yeah, I would be a little suspect with making any conclusions based on this because we clearly have some problematic data. I would probably want to gather a little bit more data before performing this test. And look, we've got some high outliers there. And in the Pacific data, we've got some pretty strong right skew, but no outliers. So anyhow, yeah, that's not good. So we should probably have requested that we get a little bit more data than just 19 and 22. If we had 25 and 25, we'd be good to go. But we don't have that choice for doing this problem. So we would note that we've got strongly skewed data, which might affect our decision. We've got outliers, which might affect our decision. But we're going to go ahead and perform the test anyway. But we would note the assumptions are invalid. So the test is suspect. That's an S. Meaning that we can't really rely on the results that we're about to get, but you asked for it, so here's our results. So let's fill in what we know. So for the Pacific, right, so we're going to go 131 minus 67.6 divided by the square root of 78.9 squared over 19 plus 33.3 squared over 22. Filled it all in. So now we can go stat, test, two sample t-test, and the data is in list 1 and list 2. And we were doing a one-tailed test to see if the Pacific was longer than the Tasman, and we can calculate it. And we got a t-score of 3.26. and the probability that our t-score is as big as 3.26 is approximately, what was the p-value? 0.0016. So therefore, that's much smaller than this 5% alpha level. So if the assumptions had been valid, we would have very strong evidence to reject the null. But our test is suspect, and I would want to redo it with a little bit more data.